So the next presentation will be given by Giulia Venditti from the University of Geneva.
Morning, everyone. Thank you for still being here until the last day. Thank the organizers for putting up such nice conference, and thanks Claire. She also gave chauffeur services these days, so thank you. Today I'm going to talk to you about percolating transitions in superconductors. So it was supposed to be Luca de Market, the PI of my group, on my behalf, but you have me, so instead of talking about disordered metals, I will talk about disordered superconductors. I know that there has been already a few introductions about superconductivity and BKT transitions, but I also know that repetita iuvant, so I want to remind you a few key concepts that I will need to move on in my presentation, and I will present you the random impedance network model to treat percolating superconducting transition and present you our results for what concerns the understanding of twisted graphene of Moiré graphene. And if I have the time, I will also tell you about a couple of things about outlooks of this project. Let me start really from scratch. We all know by now that superconductivity is a low temperature state of matter characterized by the formation of coherent Hoover pairs, and the order parameter is can be written as the expectation value of two fermionic operators. That means that we have a constant deviation of instructions of Hoover pairs, which is what breaks conservation of particles, and this is why this transition is associated with the spontaneous symmetry breaking of the U1 symmetry, and this will be interesting in lower dimensions. We have two energies at place because this is a complex order parameter. One is the energy gap, which is related really to the amplitude of the Hoover pair and to the opening of a gap in the particle-host spectrum. But we also have the most important thing, which is the fact that the system acquires a global phase rigidity, and this is encoded in what we call the superfluid stiffness, which is really the energetic cost to break the coherence of the condensate, and that's directly related to the presence of a Meissner effect and penetration depth in the system. Usually in homogeneous system and in conventional superconductors and in bulk, we focus mostly on the energy gap because this is way smaller than the superfluid stiffness, so that's what's drive transition. However, in lower dimensions and in strongly correlated systems, this relation is inverted, and what drives the superconducting transition is really the presence of the superfluid stiffness. The other quantity that I'm going to introduce right now, you know it again, is the superfluid density, which is really related to the density, so how many superconducting carriers you have, basically. And usually, commonly, we use superfluid stiffness and superfluid density as if they were equivalent terms, which is kind of true for homogeneous systems because they are proportional, but this proportionality drops when we have percolating transitions, when we have to deal with inhomogeneous systems. The reason why superconductivity is so special in lower dimensions is that, in principle, we don't have spontaneous symmetry breaking. This because the Hamiltonian of a superconductor in absence of external fields of currents, this is pretty well explained in this review by Kratap, can be mapped, coarse-grained into an XY model. So in the continuum model, we have the superfluid stiffness and the gradient of the local phase squared. And this can be exactly mapped coarse-grained discrete exponent to a Heisenberg classical model. The problem is that in this situation, in dimensions lower than 3, the Mermig-Wagner theorem prohibits to have a spontaneous symmetry breaking of a continuous symmetry. So in 2 dimensions, phase fluctuations destroys the long-range order. The reason why fluctuations are so important in lower dimensions is that if you look at the XY model, these are the pseudospins that represents basically the phase in the context of superconductor. If you have a phase fluctuations, for instance, a thermal phase fluctuation, then the spins will have no problem in following it, and we end up in another ground state, which is still a state. So averaging over time, the order parameter is 0. This is why we don't have a net magnetization in the Heisenberg way. But we can have quasi-long range order because of the Brzezinski-Kosterlitz-Thouless topological phase transition. In this case, the U1 symmetry is still preserved, but this phase fluctuations acquires the form of vortex-antivortex pairs, which are bounded below the critical temperature and proliferates for higher critical temperature. We already saw this. I'm just repeating. And the reason why this works, in particular in superconductors, this is a way bigger symmetry class. This encodes every U1, every system in the U1 symmetry class. So everything that you can somehow map with these nice arrows. This is in superconductors, the superfree stiffness is related to the square of the order parameter, and this is why we can talk about it in superconductor. The smoking gun of the transition is the jump of the superfree stiffness. So if your system has some whatever dispersion of the stiffness in 3 dimensions, in 2 dimensions, when we lower the dimensionality, when we cross this universal 2T over pi critical line, the stiffness should have a sharp jump. And this is the fixed point of the PKT topological phase transition. However, when we are dealing with true superconducting systems, a lot of stuff happens there, and in particular, we always have disorder, which is almost unavoidable in low-dimensional systems. We already saw, in particular in several talks on Monday, that if you have uncorrelated disorder, point-like impurities, you can still observe a jump in the superfree stiffness, and that means that this crossing point, the appearance of a coherence in the superconducting state, is physically related to this binding of vortex-antivortex pairs. The problem is that when the disorder appears on a mesoscopic length scales, and in particular, when you have correlations in the disorder, this can give rise to a very different mechanism driving the coherence in the transition, which is a percolating mechanism, and it can give also some exotic features in the alleged exotic features in the stiffness. So in this case, the critical temperature, so the temperature at which you start setting your quasi-long-range coherence or long-range coherence. In this way, it will be the percolating temperature and not this. So the mesoscopic inhomogeneities will mask or even completely cover signs of this vortex-antivortex unbinding. The reason why this happens, the mesoscopic inhomogeneities appears, are really material dependent. They can be intrinsic, meaning that you can have, for instance, phase competitions, or as in the case of LAUSCO, you have this, what do they call it? The confinement, the confinement potential itself, that can create local phase separations. You can have ionic gating, so there can be several mechanisms, intrinsic or extrinsic. But the overall phenomenology is quite general, and it's important to study that, in my opinion, because in this way we can really disentangle which are disorder-induced effects, which are not bad because I like to study disorders, so I think it's cool anyway. But we want also to disentangle it from genuine quantum fluctuation, from genuine quantum states. And this was already mentioned during this week. One of the reasons is that we also would like to understand from the stiffness, for instance, if you have a gapped or a nodal symmetry. Let me remind you that, so if you have an S-way, so a completely gapped system, the behavior of the stiffness will have some arcotangent behavior, whereas for a nodal symmetry, so a D wave, a P wave, etc., you expect to have a linear in T behavior far from the completion. So we want to disentangle such effects, and say at the end of my talk, I would like to try to understand what and why. Also, yesterday, I think it was during the panel, we were discussing about how we can understand nodal, differentiate nodal from gap, and this is my tiny, I'm not going to answer the question with this talk, but this is my tiny contribution to this discussion. Let me introduce you finally the model that we use. You see that I stole my my title from this nice review from Scott Kirkpatrick, Percolation and Conduction, where he introduced the random computer network. This was introduced in the context of semiconducting metal transition in amorphous systems. We're going to apply that to superconducting to metal behavior. And it consists on basically mapping your two-dimensional condensate into a sheet of resistors, which can be either metallic, superconducting, or whatever. And what we do, we call it the impedance model, because we improve the system in order to study also the finite response. So each of these guys here are now a resistor plus I omega inductance. This can be solved in two ways. So the exact solution would be to really really solve the Kirchhoff and Ohm's law on each bond and node to have the global impedance of the system. But you can also have an effective medium solution if your system is uniformly distributed and you don't have spatial correlations. There are some implicit assumptions that you made. The most important one is the fact that a single bond is large enough so you can define locally a critical temperature, a local coherence, but it's small enough with respect to the system. This is purely phenomenological, so everything that you can plug in everything, but the model by itself takes into account no phase fluctuations, only the physics of inhomogeneities and the percolating nature of the transition. So the superconducting part is encoded in the local critical temperatures. So if we have fraction W of S of superconducting bonds, the single bond will switch to its zero value if the condition on the local critical temperature is fulfilled. In other words, if we have some distribution of the critical temperature when, again, the animation. So when I lower the temperature, bonds will be switched off until you reach a percolating path where you will have your zero resistive state. If you don't have a percolating path that cuts from one edge to the other, then you will end up with a finite saturation value, which is also what is called anomalous metal. And this is just induced by the fact that you don't have percolation in your system. So the general rule of thumb is that is encoded in, if we look at the C transport, in the relative width of the transition. So if the relative width with respect to the critical temperature is over the 1, there is no way that you can understand the width of the transition just by quantum fluctuations. Instead, if this relative width is smaller, then you could have a PKT kind of transition, and you have to be careful because we already saw this week how delicate is the matter. So this model was in DC was successfully applied to understand, in particular, these large broadenings in the resistive transition, and the long tails in the resistivity also cannot be accounted by just fluctuating effect, but also this residual saturation of the resistivity, both in the LAOSTO kind of heterostructures, but also in TMDs, ion-gated TMDs, and other systems. We also showed in this work also with Prada that inhomogeneities themselves can give rise to nonlinear IV characteristics without the need to invoke for vortex-anti-vortex binding. And finally, also pseudogap signatures can be an artifact, well, not an artifact, but a consequence of strong inhomogeneities in the system. Now let's look at the superfluid response before I show you just what happens in the metallic state, the resistive part. Again, I'm not going to, there are plenty of people more, plenty of experimentalists who actually work with this kind of measurement here, so don't ask them about the details of the measurement, but what I can tell you is that the random impedance network can be compared with resonant microwave transport. So basically, the total complex conductance that we measure can be compared with the one that is measured, where I remember you that the imaginary part is directly related, is a direct measurement of the superfluid density, of the superfluid stiffness. Sorry, I did my mistake. And in the ideal situation, you would have a sharp resistive transition, some superfluid stiffness that goes up in whatever way determined by the microscopic details of your system, and the sigma 1, which is related to the unpaired electron, should have a peak at the transition and then go to 0 below and above the temperature. We already saw that with this technique, it is possible to trace down a BKT transition. So we saw this this figure already Monday in case of Strongstock, but also in KTO, there was a BKT fit. So, however, with the same exact technique, here is also, I'm presenting you KTO, because these measurements were done in the same group as this one, which is the group by Nicolas Berjal, who also gave a lecture last week about oxide interfaces. And in this situation, you see that you would have very exotic properties. How much time do I have?
You have 7 minutes. Oh.
And we tried to very slow, and from the random impedance network, we were able to understand this behavior just by considering inhomogeneous system, and in particular, this allowed us to, the sigma 1 allowed us to reveal how different responses that we had different responses of the metal and the superconducting cluster. And we go now. Let's look at what happens in twisted multilayer graphene. So in this case, 2 questions remains: what form of disorder do we have, and what is, can we say something about the superconducting order parameter? And this because there were some claims of nodal symmetry from this kind of, exactly this kind of measurement. And in this system, we have the problem of triangle inhomogeneities in multilayer graphene. And you can see that, for instance, in this paper, they talk about magic angle graphene, but if you look at the distribution of the twist angle, they're not centered at the magic angle and they have a finite width. So how do we try to understand all of that? What we do, we think about the system in a very simple way. So let's consider just an elastic solid. If you take a two-dimensional elastic solid and you just move one atom from its, you just spin one or two atoms from their equilibrium position, this will create some ripples across it. And this is exactly what we do. This is just Landau-Lifshitz book number 3, I guess, the one about solid, elasticity of solids. So if we have local uncorrelated forces, which are completely random, completely white noise, then they will create spatial displacements in a correlated fashion, which we can then compute as local twist angle inhomogeneities. And these twist angle inhomogeneities are always logarithmically correlated. That means that even for a homeopathic amount of impurities, you have long-range correlations. That happens already if you have 2 impurities. And so we take those, we map those twist angle inhomogeneities into local critical temperatures using this phenomenological formula. That means that you have this dome, which goes from 0.8 to, this is, the magic angle is at 1.1 in this case. And you have some we have some distribution of the local delta theta, but of course, this can be also here. So we basically we modify the parameters of the average and the width, the variance of this distribution, and we compute the random impedance network on top of that. That means that for the maps that we generate, we will have some induced critical temperature distributions. And this, let's see quickly the results. So if we have here, let's focus on the superfluid stiffness, which we assume now to be gapped. So we assume as wave behavior because we want to disentangle what is trivial from what is disorder induced. And if you do that, you see that for exceptionally clean systems, exactly at magic angle with a super tight distribution, you see that the distribution of the TC is almost a delta-like thing. In this case, you would be able to see both the jump of the BKT and also whatever is your shape of the stiffness, which would give you informations about the nodal or gap or whatever quantum effect you have at the microscopic level. However, when you start having inhomogeneities, so we move away from the magic angle and we start increasing this variance, then the situation gets more different, and you can have, you see that that you can have this exotic, these are just the snapshots of some configurations here in the stiffness. You cannot see it, it's pretty clear, but there are error bars because we average over 100 configurations. And you can see that you can have linear behaviors just coming from the disorder. And also, if we compute the superfluid density, the dashed dot line, you see that the two quantities are not anymore, this is what I was saying at the beginning, they're not anymore proportional to each other. So with that, you would tell me, yeah, but you're killing the field. In this way, we'll never understand anything. However, what I would like to propose is instead that until now, we never looked at the sigma one. which is really a key diagnostic feature in such experiments. And in fact, this gives information about the unpaired electrons, so it can somehow quantifies the difference between stiffness and density. You can see here in this orange yellowish how the sigma 1 goes from a peak at the superfluid stiffness, and then it broadens out, and it also saturates to a finite value. And most importantly, this also gives you information about how much correlations you have in the system, because if you have just an effective medium approach where you take into account the same distribution but with no spatial correlations, the peak is always centered at and believe me when I tell you that this is always peaked at the percolation temperature of the effective medium system, and it's pretty different and is always symmetric, whereas the correlated sigma 1 is asymmetric, is not a peak, it broadens out. And with that, I don't know what happened, so let me just flash you an outlook about studying, applying this kind of approach to a superconducting insulated transition. With this, I just thank my former group in Rome and my actual group in Geneva, especially Luca De Market, and I'll just leave conclusions and outlooks here, and I will be happy to take questions. Thank you.
Thank you for the talk. I still didn't quite get the idea of, say that if we look at a certain experiment, how do we know that the transition that you see is BKT versus percolation?
If it's BKT, is a sharp jump. That's the quick
sharp jump of
the superfluid stiffness when crossing the 2T/pi critical line. You can have slight, so for instance, in the this cluster, just in this work here, we show the examples of an NBN system where the jump is pretty sharp, and there are plenty of works in niobium nitride by Prata, by Strong. You see that here, if you do, so I don't know if you see this dashed line is the BCS behavior, and you see that there is the data at some point moves away from.
But actually, in physics, there is no such thing as infinitely sharp. I mean, superconducting transition is often pretty sharp, but there's always some line. So then, you know, what should one compare?
So in 2D, first of all, there you always have a rounding for the reason that I said at the beginning. So in this, the superfluid stiffness is smaller than the gap. That means that you have pre-formation of Cooper pairs that already rounds up the resistivity, which is not sharp anymore as in 3D. That happens in 2D. And I showed, so for instance here, you can see that there is a jump of the data. This is the renormalization group fit, and this is the BCS. Did I answer your question or?
No.
No.
Because the question is again how to separate percolation from BKT, and then you say that BKT is sharp, but it's actually not so sharp. So I don't know, but okay, maybe
you want to.
Yeah, no, there are many ways to identify that. So one thing is, of course, if you have to see a jump. Now, if you see something that is very wide and broad, you are not seeing BKT, but as you say, it's a qualitative judgment. So now quantitatively, what do you do? Quantitatively, what you have to do is you have to calculate you have to fit this data with RG or with, let's say, superfluid density, and also the temperature variation of resistance. Both you can use Nelson-Halperin to fit them. And then the fugacity that you will extract from both the data has to be the same. That is the proof that it's a BKT. There are plenty of data where people just measure resistance, do not measure superfluid stiffness. They fit the resistance data, but from that fit parameter, if you calculate the fugacity, you will get a ridiculous value of fugacity that doesn't make any sense. But if you constrain it with superfluid stiffness measurement on the one hand and resistance measurement on the other hand, fit both the data and show that the fugacity that you get in both cases are the same, that is the only.
And
Yeah, so this is the
it's one of
this
the
is what we had shown in that
Yeah.
2019.
Yeah, exactly. And the fact is that if you use, when you fit the resistivity, you have your fitting parameters are not completely free. They're always related to your resistive state. And so, for instance, for S wave, you have that this K should be of the order 1 and this B is around 0.1, more or less. If you find that B is 10, something is wrong.
So this is the problem with many of the reported reports of BKT transition into these systems. People just measure resistance and then they use the Nelson-Halperin formula that you can see here. And what they use is B as a fitting parameter, completely unconstrained, without a minding on whether the B value that you are getting is physical or not. This is something one should not do.
Okay, we have time for one last quick question from Anton.
Okay, if it's a quick one. So I didn't quite catch. In the end, you just solve your model numerically in the finite size grid, right? And
Yes.
you don't compare it, and you don't extract any theoretical features of it, like correlation length of your percolation cluster or something.
In my case, what we were interested in was really to answer the question, can we claim something about if we have nodal or not? So to answer your question, no. What I extract from my model is the correlation length of the twist angle in homogeneities from my from elasticity equations.
Yeah, but it was the input parameter for a network model, right?
It's the map. The map is the input parameter.
Yes, and then on top of it, you construct the network model, then you solve it numerically, and like looking at this solution, do you examine just the global response or something else?
I examine the global response. So I compute what I computed with the random resistor network is the total complex impedance and then complex conductance of the system. So that means resistivity in DC, sigma 1 JS.
Okay.